You are looking at thousands of tons of metal and concrete, currently suspending a massive high-speed train in midair. To the naked eye, the bridge appears perfectly solid and completely still. But if you freeze time right at the peak of the action, you realize there is a violent, invisible war of forces raging directly beneath the surface. We start with the external loads. The weight of the train pushes straight down, attempting to crush the structural deck underneath it. Engineers categorize these external pressures based on how they are distributed. The concentrated weight of individual train wheels acting on specific, narrow spots are called point loads. Meanwhile, the spread-out weight of the bridge deck itself is known as a distributed load. To keep the train in the air, the bridge must actively fight back. It generates internal resistance to counter every pound of downward pressure exerted by those external loads. If this internal resistance is overcome, the resulting failure is typically sudden. Unlike some other structural stresses, these forces can reach a breaking point without providing visible warning before the material gives way. Calculating these internal reactions is how engineers prevent collapse and determine exactly how a structure will perform under pressure. To calculate those internal forces, we have to zoom out of the macro environment and drop directly into the microstructure of the steel itself. Engineers analyze this space using a technique called the method of sections. They mathematically slice the structure open with an imaginary plane to expose the internal pressures hiding inside. This theoretical cut reveals the naked interior of the structure, specifically the thick vertical web running down the center of a steel I-beam. Here we find the beam's primary defense, shear force. This is an internal force acting strictly parallel to the cross-section, resisting the slicing action of the heavy loads pressing down from above. Down at the micro level, adjacent planes of the solid metal are attempting to slide against one another as they work to maintain equilibrium. The atomic lattice of the steel strains under the immense pressure, transferring that sliding energy from one molecule to the next across the entire section. This internal shear force prevents the metal from sliding past itself, maintaining the integrity of the beam against the gravity that would otherwise slice the structure apart. This engineering reference outlines the general rules for calculating those forces. Because shear force fluctuates depending on where a load sits on the beam, engineers must track its magnitude continuously from one end to the other. They build a shear force diagram. With no new weight applied, it draws a flat horizontal line. A point load, like a train wheel, causes a sharp vertical step. Conversely, a distributed load, like the bridge deck, forms a smooth diagonal slope. There is a strict mathematical relationship here. At any given point on the beam, the exact slope of this shear diagram is equal to the intensity of the downward load directly above it. The shear force diagram maps the exact distribution of internal stress, turning an invisible physical threat into a predictable mathematical model. As shear force acts parallel to the cross-section, it works in tandem with the bending moment, the internal rotational force that attempts to curve the beam. These two forces are locked in an integral relationship. On this secondary graph, the total change in bending moment along the beam is precisely equal to the accumulated area calculated under the shear force curve. This allows engineers to hunt for a specific mathematical target. The absolute maximum bending moment, the spot where the beam is under the most rotational stress, occurs exactly where the shear force crosses the zero line. By locating this exact coordinate on the graph, you find the physical location on the bridge that requires the most substantial reinforcement. This allows architects to optimize their materials, thickening the steel and increasing the structural capacity exactly where the mathematics prove the invisible forces are at their peak. Mastering this relationship between shear and moment is how we build structures that survive these loads. But it also raises the question, what happens to the material if those forces ever win and the steel finally begins to bend?